Yeah, hi everyone. I'm Arjun. I'm a CS master student here. I'm just here to present some work that Elliot and I have been working on this year. So basically, it's Regent-FFT, which is a fast Fourier transform written in Legion. So yeah, so maybe just to start, in case anyone's not super familiar with the FFT, so the discrete Fourier transform is defined by the equation up above. So it's basically a transform from the time domain to the frequency domain, where xn is this little xn is in the time domain and the big xk is in the frequency domain. And so the fast Fourier transform is basically a divide and conquer algorithm that's just an efficient way of computing the DFT. And so we have the input array, which is going to be divided into smaller arrays that each contain 2 points. And then for each pair of points, sum and a difference is calculated, weighted by some kind of twiddle factor. And then these points get updated and fed into the next level, which results in this butterfly access pattern that you see down below. And so this reduces the complexity, of the DFT from O of n squared to O of n log n. Yeah, so that's just an overview of the FFT. And then, so what exactly is Regent-FFT? And it's basically just a FFT library built in Regent. And so when we started this, the goal was just to have a flexible, easy to use API that allows, Regent users to perform FFT computations in a variety of different modes. And so the CPU mode is basically powered by FFTW, which is, a commonly used FFT library. And the GPU mode is powered by CUFFT. And so, we call FFTW and CUFFT functions via Terra's foreign function interface. And so there are like a handful of other parallel FFT libraries out there, and they basically all rely on these two libraries at the most basic level. Yeah. So yeah, now I'll just go over like most of the current modes that are supported. So this is basically where the bulk of the work happened. So we support both CPU and GPU modes, thanks to Regent's automatic GPU code generation. And then we also support transforms that are one-dimensional, two-dimensional, as well as three-dimensional. We can do complex to complex as well as real to complex, single precision and double precision. And then more recently, we added in batch transforms. So, if you want to perform multiple transforms of the same size simultaneously in a batch. So, if you have 7 transforms of the same size, instead of doing, calling the execute function 7 times, you can just pass in one large input region of, 256 by 256 by 7. And then we also have the first version of a distributed mode where if you have an identical FFT, executed across different nodes, we can do that as well. Yeah, so another thing that's also, I think, good to talk about is our library is also plan-based. So both CUFFT and FFTW use something that's called a plan. And so that sort of optimizes the transform for a given configuration selected. So, the plan configures the transform size, the stride, the batch size, and so on. And so once the plan is created, then, it's then can be executed based on the specifications laid out. And so the advantage of this approach is that, once you've created a plan, the library sort of retains whatever state is needed to execute the plan multiple times without needing to like recalculate things again. And so, Regent-FFT basically follows the same paradigm. Yeah, and so this is basically the library in action. So, the first thing we want to do is just create the FFT interface depending on what the kind of transform it is that we're doing. So, this is a very simple one-dimensional double to complex 64 transform. So, the parameters here are double and complex 64. And then, we have a flag for whether it's going to be a batch transform or not. And then we initialize the regions here. We then make the plan, which, I just described on the previous slide. We execute it. And then when we're done, we destroy it to free the memory. And, on the right-hand side, we can see some of the sample input and output. So this was, the arrays that we saw on the first slide. If you have, alternating 1s and 0s, it works as intended and gives us the output that we want. And so we also have, version 1 of a distributed version where, each node in the distributed job executes an identical FFT. And so, if we have, n 1D complex 64 to complex 64 transforms, each of size m, then, we can define each region to be size m times n. And then, we use regions partitioning abilities to create equal partitions where, we partition the region R into n equal size subregions. So each region is going to have a chunk of m elements. And then, when we create the plans and execute them, we also just pass the partitions in. And this allows us to do, multiple transforms pretty easily. Yeah. And then another thing that I thought would be helpful to talk about is just, we use metaprogramming to simplify our code quite a bit. So Regent supports metaprogramming, which gives us a convenient way to define similar tasks that might have different argument types. And so we use metaprogramming to greatly simplify the code and prevent the need for multiple versions of similar tasks. So on the left-hand side, we have, the original code, which basically had a different print task for every type of region that we might have had. So, whether it was a float, a double, a complex 32, a complex 34, we needed a different print task. And so, with 10 different versions of that sort of added up. And so what we did was, using metaprogramming, we just defined a parent task. And then, for each of the different regions, with just one line of code, we were able to define those. So all in all, we went from 80 lines of code to down to 20. So this was, sort of a neat way to illustrate how metaprogramming can be useful. And then another thing that I thought would be helpful to talk about is just what else is out there. As we're thinking about what to do next, we spent a bit of time seeing what other people have done. And so I think the most widely used parallel FFT library out there is P3D-FFT out of San Diego Supercomputing Center. But the main thing is that they only support CPUs. So I think our ability to support GPUs is a material benefit. There were two other GPU libraries that were out there. One was DI-GPU-FFT and one was ACK-FFT. But it seems like, as far as I can tell, both of them don't seem to be updated any longer. And then more recently in 2022, there was a GPU-FFT library that came out of IIT Kanpur. So that does support, distributed GPUs. And so, yeah, so the next step, what we're trying to think about next is, how to make our library, novel in some way, or, an improvement over what's been recently put out there. And in order to do that, I think, the next logical step, we have, the V1 of the distributed mode that, we're able to support the case where every GPU does an independent FFT at the same time. And I think that the next logical thing to do would be handling the case where we have one large FFT that's split across multiple nodes, which we cannot do right now. And, it's in progress to try to get that working. And so I think the main design choice here is whether we want to divide the data into slabs, which is basically, in one dimension, and, you have less frequent but larger communication. Or, you can do pencil decomposition, which is along 2 dimensions. And so you have more frequent, but, smaller communication batches. Yeah, so, I mean, that was pretty much it. If any of this was interesting, please, check out our repository. It's over here. We welcome any feedback. If you think this might be useful, please use it. Let us know what you use it for, and what else, might be interesting to add to it so we can work on it. But yeah.